Hi everyone, and welcome back to a new video. Today, it's the last time I talk about nucleophilic acyl substitution, and we will focus on acid catalyzed hydrolysis of amides and base catalyzed hydrolysis of amides. So before starting, it's important with amides to understand that our leaving group is this amine here, and because this amine is a strong base, so when it leaves, in this case, it's going to be a this is a strong base, so it is considered a bad leaving group, because a good leaving group is a weak base, right? So this is not only a bad leaving group, but it also acts or does resonance with the carbonyl group here. Its lone pair can resonate, and this stabilizes not only the molecule, but it stabilizes our electrophile, the carbon of this carbonyl group, our electrophile, it stabilizes it. So this is why this carbon here is considered a weak electrophile. So just like esters that we've seen in a previous video, we need to protonate the oxygen of the carbonyl group, so this carbon here, our electrophile, get a positive formal charge, and with this positive formal charge, it's going to become a stronger electrophile. Thus, it will be able to attack and start the substitution. So the first step is, like I said, the protonation. So the lone pair on the oxygen is going to grab a proton on this acid here, giving us a resonance structure. Giving us a resonance structure. And this is why I said that carbon would have a formal positive charge, right? Because here we can see that there's resonance. We can move this pi bond. We can move it to become a lone pair on the oxygen, and then the positive charge comes here, right? So there's resonance occurring here, and then in one of the resonance intermediate, we have a formal positive charge on the carbon or the electrophile or the electrophilic carbon, right? So this opens the door for the nucleophile, water, to attack. With that, we obtain this with a positive charge. And now we want to get rid of that positive charge, right? So one thing we do is have a base. This base is going to grab the proton, allowing this bond to come back and be a lone pair on that oxygen, giving it a neutral charge. All right, and then we have H3O plus leaving here. All right, now that we have this, one thing left to do is to protonate our leaving group. This here. To protonate, we need an acid. And this lone pair is going to grab this proton and protonate. This is because this group leaving would give us this one here, or this anion, which is too strong of a base. And we, as a leaving group, the better leaving group is the weaker base. So we want to protonate it so it leaves and becomes a better leaving group. So we then do this, and now that it's protonated, we have CH3, and it is positively charged. So it is then ready to leave. All right. And then with this then ready to leave, we have a carbon here, so H, and this R, and we still have this positive charge here. And we also have and the only thing we have left to do is to deprotonate this proton and this bond to lower down. So, oh, sorry. Water will be used to deprotonate. This will go here, giving us our final product, which is our carboxylic, acid. So this is the acid catalyzed hydrolysis of amides. Now for the base catalyzed hydrolysis of amides, it is much, much simpler. Now, even though I said earlier that this carbon or this electrophile was a weak electrophile, this carbon here, it only needs to be protonated if the nucleophile is a weak nucleophile. In this case, water is a weak nucleophile, and for you to understand, or for you to locate if it is a weaker, stronger nucleophile, I strongly recommend you to try and locate if the nucleophile is negatively charged or neutrally charged. In this case here, the base catalyzed hydrolysis of amides, a base is always a strong nucleophile. In this case, the minus is on the O. So it being a strong nucleophile, this oxygen of the carbonyl group doesn't need to be protonated. The nucleophile is going to attack the carbon straight up, giving us this tetrahedral intermediate, because this goes up to a lone pair, and then we have CH3, and then we have our OH here. Now, one thing to do is this here is going to leave. It's the leaving group. And then this one is also going to lower down. So we are left with carboxylic acid. But in this case, the base catalyzed hydrolysis of an amides, the product isn't a carboxylic acid, but it is in fact a carboxylate anion. And you'll see why, because we obtain, and this nitrogen is negative, and it's going to react to an acid-base reaction with this carboxylic acid, taking its hydrogen, and then this bond's going to go on the oxygen, making it a carboxylate anion, sorry. And this is our final product. So at the bottom we have the base catalyzed hydrolysis of amides. At the top we have acid catalyzed hydrolysis of an amides. I strongly recommend to first off locate you have an amide, and because this is a poor leaving group and it acts and does resonance, so it stabilizes the carbon, I strongly recommend you to then look at the nucleophile. And if the nucleophile is a weak nucleophile, then this oxygen is gonna have to be protonated for you to activate or strengthen the electrophile, or the carbon here, the carbon of the carbonyl group, to strengthen it as an electrophile, so the nucleophile can then attack. If you have a strong nucleophile, then the strong nucleophile can attack immediately and start the process. But if it is an anion, if it is a strong nucleophile, then you'll obtain here carboxylate anion as a product. All right. I hope this was helpful. If you have any questions, just let me know in the comments. All right. Thank you very much for watching.